Hi everyone, we are HBO2. My name is Meera.
And Eva.
And I'm Kaustubh.
We designed a fully differential photoplethysmogram or PPG based heart rate and breathing rate monitor for our VLSI Design Lab Spring 2024 project. We are currently recording our breathing rate measurements. As you can see on the little stopwatch, Ava's been letting the circuit charge up with her breathing rate measurements for over a minute now, and you can see the analog LPS output and the digital output from the comparator. The frequency is around 200 to 300 millihertz. That corresponds to 12 to 15 beats per minute.
The reading over there is not consistent.
We are now measuring our heart rate. Kaustubh has inserted his finger into the sensor board, and the reading on the sensor board's display is around 92 beats per minute, and the reading on the Apple Watch is around 93 beats per minute. I'm just zooming in.
78, 79. Accurate. Extremely accurate.
Extremely accurate. That's awesome.
You can even see the nice.
Yeah. The yellow is our low pass filter output, and the comparator output is green.
There is a shape to these PPG signals, right? I don't know if you read the papers, but you can actually see the shape here.
Yeah.
It has this pedestal.
Our process is based off of the reflective PPG process. This means that the LED and photodiode are on the same plane. The finger goes on top of both components, and the LED shines a light into your finger. The pulsatile blood in your finger will reflect the light into the photodiode, and the photodiode then produces a photocurrent which contains the frequency of your heart rate and your breathing rate. This is the current that is fed into our system. Our full signal chain starts from the sensor board, which sends a photocurrent into the PCB that houses our chip. Our integrated system then outputs a 3.3 volt square wave of a singular frequency into the Arduino. The Arduino reads the frequency and outputs it on the display in form of beats per minute or breaths per minute. This is a sensor board that we are sourcing our signal from. It contains green, red, and IR LEDs and photodiodes on the bottom layer for easy access with a finger. It runs on a 2.5 volt supply and outputs a photocurrent that is AC coupled into the chip via external passives. Now this is a high-level look at the testing optimized PCB where our signal is fed into. The PCB contains the socket where our chip lives and the connections for our two signal chains. We have separate LDOs powering each signal chain, providing our 1 volt supply. This means that we can turn on one signal chain while the other is off and vice versa. After the signal is input and processed by our chip, the PCB also handles the interfacing with the Arduino. To do this, each signal chain has their own level shifter that converts our 1 volt square wave output into a 3.3 volt signal that can be read by the Arduino. And last but not least, the rest of the PCB is reserved for pinouts to test intermediate nodes and the necessary passives.
So now that we've given a brief introduction into how our measurement setup works and how it looks, let's take a look into the inside of the chip and see how it helps us achieve the things that we've discussed earlier, like how does it measure the breathing rate and the heart rate. So the figure in this slide shows the pictorial representation of the measurement setup that we just showed you in the video and in the slides. So if you take a look from the left-hand side, the measurement setup basically has LEDs, both red and green, and there's a place where you can like place your finger on the LED, and the signals that are reflected from your bloodstream go onto the photodiode, and the AC information corresponding to the breathing rate and the heart rate are encoded in the AC response of the signal. So, and the DC is not really necessary for us to process the heart rate and the breathing rate, which is why we filter it out using a DC blocking capacitor. And you can see the signal levels after the DC blocking capacitor as shown in the signal diagrams in this figure. So at this point, both the heart rate and the breathing rate signals are essentially the same. And as you can see, the breathing rate and the heart rate signals are so low that they're very close to the noise floor. and these need to be amplified and filtered out so as to get their corresponding outputs to the Arduino. And you can see there's like an interference at 60 hertz, and this is coming from the supply. So what our chip essentially does is amplify these signals and suppress the interference so that we can get a proper waveform at the output. So here's a block diagram of our chip. So our chip essentially consists of three different blocks. One is the transimpedance amplifier. There's like an amplification and filtering stage, and there's a comparator. So the transimpedance amplifier converts the current that is coming out of the photodiode into a voltage, and then that is later on amplified and filtered out by the filtering stages. And later on, uh, so far this gain amplification has been like a linear has been is in a linear fashion, but from this point onwards the comparator does like a nonlinear amplification and sends 0 to 1 square wave signals out of the chip. And as you can see in the signal diagram at this point, the heart rate is amplified in the heart rate path, and the breathing rate is amplified on the breathing rate path, and the 60 hertz interference is suppressed. And these signals are processed onto the Arduino, where they are counted and displayed on the LED. And as far as the specifications for both of these paths are concerned, the TIA feedback resistance for both the paths are different because we need higher gain for the breathing rate. Whereas the bandpass and the low pass filter have the same gain, but they differ in terms of bandwidth. That is, the heart rate path has a bandwidth of 0.6 to 4 hertz, whereas the breathing rate has a signal bandwidth from zero point 0.2 to zero point 0.4 hertz, and this is ensured so that we can get the right signal in the right path and amplify it as we go along. And the hysteresis and the supply for both these paths are the same, where the hysteresis is mentioned for the comparator.
Now let's look at the first stage of our system.
Once the photocurrent is generated by the sensor board, it is AC coupled and fed into the single-ended transimpedance amplifier, or TIA for short. The TIA performs three functions at the stage. First, it converts the current signal to a voltage, then it contributes to the gain stages by amplifying the signal, and finally it biases the output at 500 millivolts.
So now that we've seen how the transimpedance amplifier has been designed, let us take a look into how the amplification and filtering stages have been designed using a bandpass and a low-pass filter. So this is the block diagram of our entire heart rate path, and the amplification and the filtering stages have been performed using a bandpass and a low-pass filter, whose block diagrams are shown in the figures below. So these filters have been designed using Tau Thomas biquads, and these particular biquads use fully differential amplifiers that have been implemented on chip. And depending upon the path of either heart rate or breathing rate, we decided to design the passives on chip or off chip depending upon their values. So, and the passives that are related to these filters helping setting the signal bandwidth corresponding to each of these paths. And since the frequencies that we're dealing with are so low, around the order of 1 hertz, all the capacitors are off chip since they're like 1 microfarad, and given the area constraints that we have, these cannot be designed on chip. And as far as the heart rate is concerned, the values were manageable so that we designed them on chip, whereas for the breathing rate, all the passives are off chip. And now that we've seen things from a system level, let us take a look into how this particular fully differential amplifier has been designed on chip. So here's the schematic of the fully differential amplifier that was implemented on chip. So essentially, this fully differential amplifier has 4 blocks. It has a master current mirror stage, a first amplification stage, a second stage, and there's another amplification stage, which is the common mode feedback amplification stage. So as far as the current mirror is concerned, there is an external voltage pin that supplies voltage, which helps in setting the current through the first stage of the amplification. And this current is fed at the source of the first stage, and differential inputs are applied at the NMOS pair of this first amplification stage. Their outputs are then taken from the drains of the NMOS transistors and fed into the second stages. And since there is no mechanism that sets the DC voltage at the outputs of the second stage, there's a necessity of designing another amplifier, which is the common mode feedback amplifier. So this particular common mode feedback amplifier takes the output from the second stage and feeds them through an RC network, which basically compares it with the external supplied voltage and sets the DC voltage of the second stage. So in this case, since we're dealing with a supply voltage of 1 volt, the common mode voltage that is coming from the external supply is 500 millivolts, and the CMFBA essentially sets the outputs to be at 500 millivolts and also suppresses common mode signals. So let us take a look at the simulation results from this particular FTA. So the figure on the right shows you the DC gain of the FTA under a unity gain feedback condition. So these simulations depict process variation, and essentially the FTA is designed to have like a 60 dB DC gain, whereas the UGB for this or the zero crossing over point for this particular FDA is not a design constraint, since the signals that we're dealing with are so low. So the 3 dB bandwidth can be as high as possible, and we've essentially over designed this for this FDA. And the common mode feedback amplifier has a DC gain of around 60 dB, which is good enough for us to ensure that the outputs are settled at 500 millivolts. So using these FDAs, the bandpass and the low-pass filters were designed. And as I mentioned earlier, for the heart rate, all the resistors for the breathing rate, for the bandpass filter and the low-pass filter were implemented on chip, whereas for the breathing rate, all resistors and capacitors are on the PCB. So this slide shows you the simulation results that have been simulation results for the heart rate, BPF, and LPF. So the curves in yellow and blue are the ideal filter response, essentially the responses that are coming out of a completely ideal simulation with ideal amplifiers and passives, whereas the curves in red and green show you the LPF and BPF results that we have got from the designed amplifiers, like the design amplifiers, as in the on-chip implementations of these amplifiers. So as you can see, there's like a bandwidth reduction compared to the ideal cases. This is slightly expected because the ideal cases do not take into consideration the parasitics that are involved at every node. But even with the slight reduction in bandwidth, it is good enough for the signal bandwidth to pass through, which is around 0.6 to 4 hertz. So that concludes the filtering section of this presentation.
The comparator is the last block in our signal chain, and the comparator essentially functions as a sine wave to a square wave conversion block so that we can get a 1 volt rail-to-rail output at the end of our signal chain, and this can be used as a digital signal for the rest of our post-processing techniques. The comparator makes use of a differential input signal and 2 reference input signals against which each of these differential signals are compared. And based off of the amplitude that the differential signals carry, we are able to either achieve a logic 1, which corresponds to a 1 volt value, or a logic 0, which corresponds to a 0 volt value. What you see in front of you is a schematic of the comparator. The comparator is fully differential and it has a current steering architecture. One of the main features of the comparator is its ability to achieve hysteresis. Hysteresis is accomplished through the cross-coupled PMOS current mirror that the comparator has. We have provided source degeneration resistors in order to improve the linear input range of the comparator. And we've also done a single-ended, the differential to a single-ended conversion at the output as well. The comparator outputs, in order to boost their rise and fall slopes, inverter buffers have been provided at the end of the comparator, after which the output is extracted. We use 2 kinds of simulations to characterize our comparator results. And the first simulation is a DC response, and the second simulation is a transient response. The DC response essentially measures the comparator's hysteresis widths across different simulation conditions, which are the PVT conditions.
And the transient response measures the rise and fall time that the comparator has with respect to different PVT conditions. So for a typical case, the hysteresis of the comparator comes out to be around 60 millivolts, and the rise and fall slopes are about a few hundreds of nanoseconds, which is permissible because our entire design operates at a frequency of around 0.6 to 4 hertz. And for those kinds of frequencies, a small rise and fall slope is appreciated. We will now move on to certain chip level simulations. We've performed chip level simulations with including our pad pins and bond wires, both for our pre-layout and post-layout cases. What you see in front of you is a total signal path of both the signal chains, the heart rate and the breathing rate. So the heart rate and the breathing rate signals have been tapped out up out until the chip level at the output of the TIA, at the output of the bandpass and low-pass filters, and at the output of the comparator as well. As you can see, the input has been simulated using a sinusoidal signal that falls in the mid-range of the frequency band of interest. For example, if we choose a heart rate, we've chosen a frequency of around 2 hertz, and for the breathing rate, we've chosen a frequency of around 0.2 hertz or to 0.3 hertz for that simulates the input signal value. This current input is then converted into a voltage through the transimpedance amplifier, and then this amplified voltage is then subjected to further amplification and filtering, and finally to analog to digital conversion through the comparator as observed in our signal chain. We also have a chip level floor plan that is presented. Our ideology was to maintain two distinctive power domains in order to ensure that each of the signal chains can be turned on or off independently. So all of the HR components have been placed towards the top and the left side of the chip, and all of the BR components have been placed towards the bottom and the right. In order to ensure proper routing practices, all of the pins corresponding to each of these signal chains have also been placed in accordance to the location of each of these components. You can also see a snapshot of the layout and the die photo of the entire chip. As you can see, different components are visible over here independently, and we've also made use of supply decoupling capacitors in whatever area that was remaining in the chip. We've also conducted post-layout transient simulations in order to verify if any parasitics that have been introduced in our layout process have severely affected the performance of our chip. As you can see, the circuit has been simulated in this case with an input signal which corresponds to our frequency of interest, along with a noise signal which we anticipate would exist at 60 hertz, which is a function of our power supplies. As you can see, the heart rate simulations have been carried out successfully on this slide, and you can see the outputs from the transimpedance amplifier, the bandpass and the low-pass filter, and also from the comparator as well. We also carried out the same set of simulations for the breathing rate circuits, and we've also obtained a proper functionality test. Naturally, there is certain amount of delay between the input and between the pre-layout and the post-layout simulations, and this is in accordance with our expectations because of the addition of all of the parasitics that are associated with different components of our chip.
This entire board here is going to be our measurement setup. We have a sensor board, we have our main PCB, we have our Arduino, and we have a display. So how we capture our input signal is by placing our finger inside the sensor. We are then able to generate a photocurrent that is then passed on to the chip. The chip has our amplification and filtering stages, and the amplification and filtering stages convert the photocurrent into a voltage, and they amplify, boost it, and remove noise and send it as the output. The output is then level shifted to 3v3 volts and then supplied to the Arduino. The Arduino is then programmed to count the number of rising edges in order to calculate the frequency, and this data, which is calculated separately for the heart rate and the breathing rate, is then sent to our display where we can see the data in real time. We also have provided several header connections and jumpers so that during the process of our testing and verification, we're able to see different outputs in the intermediate stages of our amplification and filtering process. And we're also able to program the gain, the bias currents, and other passive components that are required to attain the tuning and the gain that we require. We can also see that the chip is present inside the socket here, and we also supply decoupling capacitors around the chip.